So let's consider this question on fluid mechanics just to also explain the concept of energy gradient lines and hydraulic gradient lines. The question says a pipeline ABC connecting two reservoirs is 80 mm in diameter. From A to B, the pipe is horizontal as shown in the image below, and from B to C, it falls by 3.5 mm. The lengths AB and BC are 25 meters and 15 meters respectively. If the water surface in the reservoir at A is 4 meters above the center line of the pipe and at C 1 meter above the line of the pipe respectively, question says calculate the rate of flow and neglect the loss at the bend but consider all other losses. Also draw the energy gradient line and hydraulic gradient lines. Take dicey friction factor F to be equal to 0.024 and K entrance to be equal to 0.5. Alright, so just like the question says, although we're not presented any given image or diagram, but we can easily formulate an image or diagram given the condition in the question. So let's plot out the image and see how this image looks like. So we have a reservoir, okay, connected to a pipeline. So we can simply have this to be the pipeline. Okay, let me make it faint. All right, so I'm making this faint because of the condition, a particular condition that was given in the question. So I'll make that pipeline faint, but this is our reservoir. All right, so just a rough sketch. Now, from the question, it says that the pipeline connected to this reservoir is 80 millimeter in diameter. So we expect that this pipeline is 80 millimeter in diameter from A to B. Now, along the line, it falls by 3.5 millimeter. So if it falls by 3.5 millimeter, it means that one end or one portion of both portions of the pipeline from one end falls by 3.5. So we can have from here to be 3.5. We can have from here to be 3.5. So that means we have a different pipeline altogether with a different diameter. Alright, so the diameter of this pipeline is 80 millimeters. So let's get this out. This is 80 millimeter diameter. So call that diameter D1, whereas the diameter of the second pipeline now becomes, remember, this falls by 3.5 millimeter. So from here to here is 3.5 millimeter. Let's indicate that here. Okay, and from here to here is also 3.5 millimeter. So this is also 3.5 millimeter. So which means if you add them both, 3.5 plus 3.5 gives you 7 millimeter. So in order to obtain this diameter, it simply means what? Remove 7 millimeter from 80 millimeter, which is diameter of the bigger pipe. So 7 or 80 millimeter minus 7 millimeter obviously gives us 73 millimeter. So the diameter of this pipe is actually 73 millimeter. So you have this. Okay, so that's the first thing to do. Remember, the one that has 80 millimeter diameter is pipe A to B, whereas from B to C has now this new diameter, or which falls by 3.5 millimeter. Okay, so having done this now, next thing is to outline the length or impute the length. Question says that the lengths AB and BC are 25 meters and 15 meters respectively. So for pipe AB, this is from A to B. The length from A to B is actually 25 millimeter. You indicate that, sorry, 25 meters, whereas from B to C is actually 15 meters. Now, the next thing to find is the height difference. The question says if the water surface in the reservoir at A is 4 meters above center line and at C is 1 meters. Okay, all right, so this is the center line of the pipe. You have something like this to be the center line of the pipe. All right, so this is the water surface in the reservoir. All right, so you can simply call this the water surface in the reservoir. So the height from the center line to the water surface was given as 4 meters, whereas that's for the first pipe, that's from pipe A, whereas from pipe C, okay, whereas from pipe C, from the center line to pipe C, now notice that this is pipe C, from this point to this point indicates pipe C, which is this height difference after the fall. So this other height difference here was given to us as 1 centimeter. Mind you, this is called Z1 and this is called Z2. So the first height Z1 is 4 meters, the second height Z2 is 1 meters from pipe C. So you have this, okay. So this is now the whole information given to you in the question. That's the diagram. So all we need to do now is to now solve for which the first question says we should calculate the rate of flow. That is simply saying we should find the discharge. That's what the question is asking us to find. Find the discharge. Now they ask us to neglect loss due to bend, but we should consider every other losses in the pipe. Although in this question there's no bend, so there's no need to bother ourselves about loss due to bend. But then we have to now consider all the losses. But to solve this question, the first thing to do is recall that discharge, this is what we are asked to find now. Discharge Q is actually what? Area times velocity. Since we know the diameters of the pipe, diameter of pipe 1 and diameter of pipe 2, it means that we can find their areas. Okay, so this is pipe AB and this is pipe BC. So we know their diameters, we can find their area. Diameter of pipe AB was given to us in the question as 80 millimeter. So we convert this to meters, simply dividing 80 by 1000, and that will give us 0.08 in meters. This is diameter of pipe A. So which means we can find the area of pipe AB, area AB. So simply AAB, and area is simply pi times diameter AB all squared divided by 4. This is now equal to pi has a constant value 3.142 multiplied by diameter itself now is 0.08 all squared divided by 4. You have this. So from here you can find the area of pipe AB to now be equal to, let's compute all of it this at once to save time. 0.08 squared multiplied by 3.142 divided by 4. So we have that area to be 5.8272 by 10 to the power of minus 3. 5.8272 by 10 to the power of minus 3 in meters squared. So this is the area of pipe AB. So with this area, you can actually find from continuity equation, discharge in pipe AB equals discharge in pipe BC from continuity equation. For the flow to be continuous through the pipe, the both discharges are equal. So that simply means you can easily choose to make discharge of pipe A to be the whole discharge in the pipe or the flow rate in the pipe. Okay, having that in mind now, so our flow rate, which is discharge Q, now we're considering discharge of AB, is now equal to area of AB times velocity of AB. Now, we don't know this velocity, but we know the area, so we can simply say that discharge AB is now equal to area gave us 5.02. All right, so the area is 5.02, please. Area is 5.0272 by 10 to the power of minus. So that gives us the area. So if we know the area, we can now compute here. All right, so we have in place of area for area is 5.02, please mind if allow mistake. So we have 5.0272 by 10 to the power of minus 3 times velocity A B. So this is now the discharge or the flow rate we are asked to find, but we don't know this velocity. That is where we have to now apply or consider all the losses involved. So let's take a look at the diagram once more. As the fluid flows, and enters into this pipe, there is a head loss. As the fluid is entering into the pipe, the first pipe has a velocity, which is velocity that is in this pipe AB. We can call that V1, call the speed of flow here V1, call the speed of flow in this pipe V2. So instead of using VAB, we can simply call that V1, and instead of using VBC, you can simply call that V2. Okay, so the first speed is of course V1, that's the speed of flow in this pipe. As the fluid enters into this pipe, it experiences a head loss, which is called head loss due to entrance. So we put that down. That's the first head loss we consider. head loss due to entrance. Okay, so we are considering the losses now. The first is head loss due to entrance. Now the formula is actually HE, where H stands for head loss, E stands for entrance, is equal to, naturally, the formula is 0.5 V squared. Now V becomes the speed at that particular pipe. Since it is inlet or entrance, we call that V1, okay? V1 all over, that's the first speed in the pipe, all over 2 times G. But most textbooks actually use K V1 squared all over 2G for entrance, but this K automatically always is 0.5. That's why if you look through the question, it was also given in the question, take K entrance to be equal to 0.5. It was given in the question, so always it is given as 0.5. You have to know that as a constant term. Since we don't know V1, okay, since we don't know V1, we simply write that head loss due to entrance is equal to 0.5. V1 is unknown, so call that V1 squared all over 2G. 2 times G is 9.81 from gravity. So this is actually 0.5 V1 squared all over 2G. 2 times 9.81 is 19.62. That gives you 19.62. So let's obtain now 0.5 divides 19.62. This will give us the head loss due to entrance to be equal to 0.5 divides 19.62. We have 0.025, 0.0255 V1 squared. Now let's call this equation 1. Let's call this equation 1 and let's fall back to the discharge equation, please. Let's fall back to the discharge equation. So remember I said that discharge in pipe AB equals discharge in pipe B. So this is from continuity equation. Okay, this is from continuity equation. So for the flow to be continuous in the pipe, their discharges must be equal, and we obtain that discharge in pipe AB, okay, QAB, we said it is area of pipe AB multiplied by the speed of pipe AB. Now the speed of pipe AB is something as V1, that is the speed in pipe AB, the speed of flow through this pipe A and B, we'll call that V1. Okay, alright, so if we have that and we already solve for the area of pipe AB, we obtain 5.0272 by 10 to the power of minus 3 V1. We call this the discharge. So instead of VAB, call that V1. Let's also find discharge in pipe B. QAB obviously becomes, discharge in pipe BC. So QBC obviously becomes area in pipe BC multiplied by velocity in pipe BC, which in this case now is V2. Okay, or you can simply say A BC times VBC. So VBC, velocity of flow in pipe BC, is something as V2. Alright, so what we need to do now is we have to now find the area of pipe BC. Now recall that diameter of pipe BC was given to us to be equal to, we obtain 73 millimeters. So we convert this to meters, divide 73 by 1000. That simply gives us 0.073 in meters. So we need to now find the area. What is now the area? Area of pipe BC is now pi diameter of pipe BC all squared divided by 4. Pi itself is a constant value 3.142 multiply diameter give us here 0.073 all squared divided by 4. So I'll punch everything at once. So area of pipe BC is now equal to, so you might do well to also punch along to notify if there's any error. Okay, 0.073 all squared multiply 3.142 divided by 4. That gives us 4.1849, 1859, please. Okay, by 10 to the power of minus 3 in meters square. So this becomes the area. So if that's the area, therefore discharge in pipe BC is now equal to, we said it is simply velocity of pipe BC times the area. The area is simply this 4.1859 9 by 10 to the power of minus 4 multiplied by the velocity in pipe BC, which is V2. So you have V2. So this is the second discharge. Now from continuity equation, we said the both discharges are equal for the flow to be continuous. Okay, QAB equals QBC, and this is QAB 5.0272 by 10 to the power of minus 3 V1, and we've already obtained this for QBC. So we equate the two equations from continuity equation, equate them together. All right, so that will simply give us that since we had QAC to be equal to QBC, QAB to be equal to QBC, therefore QAB gave us 5.0272 V1 to be equal to QBC gave us, we had 4.1859 V2, okay, by 10 to the power of minus 3 V2. So all we need to do at this point is either solve V1 in terms of V2 or solve V2 in terms of V1. So let's make V1 subject. Therefore, V1 is equal to, divide through now by 5.0272. We have 4.1859 by 10 to the power of minus 3 V2 all over 5.0272 by 10 to the power of minus 3. So this now implies that V1 itself is now equal. So this helps us to find the speed in terms of the second speed of pipe 1 in terms of speed of pipe 2. So let's do it and see. Divide 5.0272 exponential minus 3. So we have that to be 0.83 V2. So which means V1 is 0.83 V2. So you keep that equation aside. Now having that for V1, let's look at the head loss due to entrance we just calculated. Considering head loss due to entrance, we obtained, that's the first equation, we obtained 0.0255 V1 squared in place of head loss due to entrance. Alright, so we had here 0.0255 V1 squared, but we know what V1 is. Let's recall it again. Head loss due to entrance, HE, gave us 0.0255 V1 squared, but we know what V1 is. V1 is equal to 0.83 V2. So in place of V1, we'll put in this value. Okay. So in place of V1, we'll put in this value, and we are definitely going to have head loss due to entrance to be equal to, this is 0.0255. This is V1 squared, and V1 is 0.83 V2. So all squared. So this is going to now be 0.0255 multiplied by, let's obtain 0.83 squared. That gives us 0.6889. So multiply by 0.6889 V2 squared. So take note, once you square here, you also squared everything in the bracket. So V2 is also squared. So we have that. So this simply implies that head loss due to entrance is actually equal to multiply by 0.0255. And we have that answer to be 0.0176. So head loss due to entrance gives us 0.0176 V2 squared. Call this equation 1. That's the first head loss. Now let's go back to the diagram. So we said once the fluid enters into the pipe, it experiences a head loss. Now as the fluid enters successfully into the pipe walls and the fluid surface are in contact. Now due to this contact, it leads to what is called head loss due to friction, because friction involves when two surfaces come in contact. So to calculate head loss due to friction, we make use of Darcy-Weisbach equation. So the next head loss to calculate now is head loss due to friction in pipe 1. So we calculate head loss due to friction in pipe 1. That's the first thing to do. Head loss due to friction in pipe 1. Now we use Darcy-Weisbach, okay? Using Darcy-Weisbach equation, okay? Using Darcy-Weisbach equation, And the equation simply says head loss due to friction is 4 FL V squared all over D times 2G. Now, since we are in pipe 1, since we are talking about pipe 1, it means the length there is length of pipe 1, diameter the diameter of pipe 1, and then the speed is also speed of pipe 1. So you indicate that in this equation, this becomes 4, okay, this is equal to 4. F is the friction factor, is a constant, given in equation as 0.024, okay. F L becomes L1 now, the length of pipe 1, V becomes speed of pipe 1, V1 squared all over, D becomes diameter of pipe 1 times 2G. So head loss due to friction in pipe 1 is now equal to 4 times F was given in the question as 0.024. So in place of F you have 0.024 multiplied by length of pipe 1 was given as 25. Okay, multiply V1. Now recall that we've solved for V1 and we obtain from the equation V1 to be equal to 0.83 V2. So we're going to, all our V1 will always be replaced by 0.83 V2 so that all the velocities will be in terms of V2. That's the essence of this. So we fall back to that equation now. Falling back to this equation, we have here in place of V1 squared, V1 is now 0.83 V2. Okay, so all squared. Remember, we have V1 squared, so you have to square this all over D1. Diameter of pipe 1 was given as 80 millimeters, so that's 0.08 multiplied by 2 multiplied by gravity is 9.81. So I'm going to compute the numerator separately and then compute the denominator separately. HF1 is now equal to, so calculating for the numerator we have, so do where to point as well. 4 times 0.024 multiplies length is 25 multiplied by 0.83 all squared. So we have 1.65336 for the numerator. Okay, 1.65336 V2 squared all over. Let's obtain the denominator as well. Denominator give us 0.08 multiplied by 2 times 9.81. So we have 1.5696. 5696. So let's divide together now. So 1.65336 divided by answer gives us 1.05 approximately V2 all squared. So this means that head loss due to friction in pipe 1, this means that the head loss due to friction in pipe 1 is equal to 1.05 V2 squared. So you keep this equation aside, call this equation 2. Now we found the head loss due to friction in pipe 2. The next head loss to calculate now, let's go through the pipe again. Now, as the fluid is leaving the larger diameter pipe to enter into the smaller diameter pipe, what happens is that there's a sudden reduction. This 80 millimeter suddenly reduces towards 73 millimeter, causing the fluid to what? Contract. Okay, causing the fluid to contract to enter or fit into this pipe. So that will give rise to another head loss called head loss due to sudden contraction. Okay. Alright, so we call that HC, head loss due to sudden contraction, and the formula remains V squared all over 2G. Now, V means the velocity at the particular place of contraction. Okay, the velocity at the particular point of contraction. Alright, so we simply call that V2. Okay, head loss due to contraction. Alright, so since this is pipe 2, okay, we are calling that V2 since this is at pipe 2. The pipe 2 is what contracted, okay, into 73 millimeters. So that becomes the speed at that point, V2. So this is equal to, V2 is unknown, all over 2 times 9.81. Remember, we are solving all our head losses in terms of V2. So it is very wise to leave V2 as this. Now this is equal to V2 squared all over 2 times 9.81 is approximately 19.62. So it's more or less you saying 1 divides 19.62. So 1 divides 19.62, that gives us 0.05 V2 squared. So we have 0.05 V2 squared. So this implies that head loss due to contraction is actually 0.05 V2 squared. Call this equation 3. Okay, call that equation 3. Head loss due to contraction. Now, the next thing to find is, let's look at the diagram again. As the fluid finally enters into this pipe, once again, there is now contact between the fluid surface and the pipe surface, leading to friction. So we need to calculate the head loss due to friction in pipe 2, also using Dicey-Weisbach equation. So we calculate for head loss due to friction in pipe 2. So we are still using Dicey-Weisbach equation. So HF2, head loss due to friction in pipe 2, remains 4F. This now L2. This is now V2 squared all over D2 times 2G. Okay, so these are parameters at point 2. So 4 is a constant. F was given in the equation as 0.024 multiplied by the length of pipe 2 was given as 15 multiplied by V2 itself. V2 we don't know, so remains V2 squared. Since we are all solving the head loss in terms of V2, so leave V2 like that. All over D2, diameter of pipe 2, we had 73, which is 0.073 meters, multiplied by 2, multiplied by 9.81 for G. So HF2, head loss due to friction in pipe 2. Okay, so I'll compute the numerator all at once. So we have 4, F is 0.024. So 4 times 0.024 multiplied by length, L2 is 15. Okay, so that gives us 1.44. We have 1.44 V2 squared divided by, let's obtain denominator. So we have 0.073 multiplied by 2 multiplied by 9.81. So that gives us 1.43226. We have 1.43226. Dividing this together will give us head loss due to friction in pipe 2 to be equal to 1.44 divided by answer. That gives us 1.005 or approximately 1.01 V2 squared. So this is equation 4. Alright, so that's equation 4 for head loss due to friction in pipe 2. Moving further now, let's go back to the diagram. Now the question says we should neglect head loss due to bend. There is no bend in the pipe. After here, what happens is that this fluid exits the pipe. The fluid exits the pipe, so that will constitute us, or that will require us to find the head loss due to exit. As the fluid exits the pipe too, we have to find head loss due to exit. So we find head loss due to exit. Okay, so head loss due to exit in pipe 2, we can simply use H, okay, EX for exit, and also that's given as V squared all over 2G. Okay, the head loss due to exit is also given as V squared over 2G, where V becomes the velocity at the point of exit. In this case now, let's go back to the diagram. The velocity at the point of exit is what? Is still V2 because it is exiting at pipe 2. So it becomes V2. Oh, okay, this is now V2 squared. Okay, so this is now equal to V2 once again unknown. So we'll leave it like that since we are solving all the velocities in terms of V1 or all the head losses in terms of V1 all over 2 times G is 9.81. This is V2 squared over 19.62. I think we've done this before. So invariably, all you're doing is 1 divides 19.62, will give us 0.05. So this simply implies that head loss due to exit is 0.05 V2 squared. Call this equation 5. Alright, so we are done with all the head losses. We need to now employ Bernoulli's equation. Now, what is Bernoulli's equation? From Bernoulli's equation, the sum of the pressure head, kinetic head, and potential head at one section of the pipe equals that at the other section of the pipe plus all the losses. So we have P1 over specific weight plus V1 squared all over 2G plus Z1, and that's equal to P2 over specific weight plus V2 squared over 2G plus Z2 plus all losses. Now, what are these losses? The losses we've been calculating so far: head loss due to entrance, head loss due to contraction, head loss due to friction, and head loss due to exit. These are all what is called the losses in the Bernoulli's equation. Now, notice that we are not given pressure at state 1 or pressure at state 2, so which means pressure is 0 and pressure here is also 0. These two are off. So we only play around with these two equations. Let's bring everything here, leaving all the losses here. Let's bring everything together. So we have here V1 squared over 2G. Let's bring this man over here. V2 squared over 2G crossover becomes minus V2 squared all over 2G plus we have Z1 here. Let's bring Z2 over here, becomes minus Z2, and that's equal to what we have here now is what? All the losses. So once again, we can take LCM here. LCM between V1 and V2, the LCM is 2G. So you have 2G all into this becomes V1 squared minus V2 squared. Okay, you have this. So plus Z1 minus Z2, and the whole of this is equal to all losses. So here is what we'll do. Remember, we already solved for V1. Recall V1, we had V1 to be 0.83 V2, not forgetting. So which means in place of V1 squared here, we can replace it with V2 to make everything, like I told you, make all velocity to be in terms of V2. So in place of V1 here, we simply replace that with 0.83 V2. So this now becomes in place of V1 squared, we have 0.83, we have 0.83 V2 all squared minus V2 here squared all over 2 times 9.81. Okay, plus, now take note, Z1 represents the surface level at pipe A and the center line of the fluid, which was indicated in the equation. I said it earlier. Z1 is 4 meters and Z2 is 1 meters from the diagram. So we have to indicate that there. So you have here, so in place of Z1 is 4 minus Z2 is 1. And the whole of this is equal to the sum of the entire losses. So let's add up all the losses. We had the first equation, head loss due to entrance, and we obtained head loss due to entrance, to entrance to be equal to 0.0176 V2 all squared. So that's the first equation. So we'll put it back into the losses now. Okay, let's fall back here, 0.0176 V2 squared. So in place of the losses, for the first loss, we have 0.0176 V2 squared plus, okay, pardon me, I have to continue from here, plus the second loss we obtained was head loss due to friction in pipe 2, friction in pipe 1, head loss due to friction in pipe 1, and we obtained the head loss due to friction in pipe 1 to be equal to 1.05 V2 squared. Okay, we obtained that to be 1.05 V2 squared. So we add that up, plus 1.05 V2 squared, plus next is head loss due to sudden contraction. So let's look for it. Head loss due to sudden contraction over here, and we obtain head loss due to sudden contraction to be 0.05 V2 squared. We'll also add it up, 0.05 V2 squared, so plus 0.05 V2 squared, plus next is head loss due to friction in pipe 2, head loss due to friction in pipe 2, and we have it here, head loss due to friction in pipe 2, we had it here to be 1.01 V2 squared, so we have it to be 1.01, so plus 1.01 V2 squared, plus finally head loss due to exits, okay, finally head loss due to exit of fluid from the pipe. Over here, we have it to be 0.05 V2 squared as well. So we'll have it to be 0.05. I'll put it down here, 0.05 V2 squared. Now, this is the essence of making all the speeds to be in terms of V2 so that we can easily add them all up and find the value of speed 2. So as you can see on the right hand side, we have all terms in V2. Also on the left hand side, terms in velocity also are in V2. So let's evaluate now and see. On the left hand side, we have to find 0.83 V2 squared. Okay, so 0.83 all squared. That gives us 0.6089. We'll have 0. That gives us 0.6089 V2 squared. Remember, minus V2 squared minus V2 squared all over 2 times 9.81 gives us 19.62 plus. Now 4 minus 1 here give us 3, and that's equal to. So let's add up all these losses. Let's add all of them together. So we have 0.0176 plus we have 1.05 plus we have 0.05 plus we have 1.01 plus we have 0.05. So the whole of that addition gives us 2.12. So the whole of that addition gives us 2.1776. So we have the whole of this will be 2.1776 V2 all squared. Okay, so you can see evaluate this further. You have here 0.6089 V2 squared minus, now this is standing for 1 V squared, V2 squared, so minus 1, and we have minus 0. Okay, this gives us minus 0.3111 V2 squared all over 19.62. Okay, plus 3, and that's equal to 2.1776 V2 squared. All right, so you have this. So let's evaluate this further by dividing through. Okay, 0.311 divided by 19.62. So that gives us minus 0.0159 minus 0.0159 V2 squared plus 3 to be equal to 2.1776 V2 squared. So at this point, the analysis becomes very easy. We can now send minus 0.015 over to this side of the equation. Negative sign cross and equal to sign becomes positive. So here we have 3 left. 3 is now equal to, so we have here 2.1776 V2 squared. This becomes now plus 0.015. Okay, 0.0159 V2 all squared. So we can add up these two now. All right. So let's get that addition. 2.1 2.1776 plus 0.0159. So that addition gives us, remember 3 is equal to 2.1935 V2 all squared. So we can now make V2 subject. V2 squared equals 3 divides, of course, 2.1935, which is equal to So 3 divided by answer, that gives us 1.3677. We have 1.3677. So V2 squared equals 1.3677. Alright, so to make V2 subject of us to take the square root, so this simply implies that V2 is equal to the square root of 1.3677. This will now give us the speed at section 2. So square root of answer is 1.17. So we have 1.17 meters per second. So this is now the speed of pipe 2. Now, if you know the speed at pipe 2, recall in equation 1, recall when we did the continuity equation, we said that V1 is equal to 0.83 V2. Now we know what V2 is. This simply means that V1 is equal to 0.83 in place of V2. V2 is 1.17. So this implies that V1 itself is equal to times 0.83. That gives us 0.97. So V1 is equal to 0.97 meters per second. So this becomes speed V1 and speed V2. Now you're asked to find this charge. You can now use any of the continuity equation. So we obtain QAB to be equal to, okay, we had 5.0272 by 10 to the power of minus 3 V1 or VAB. So we can use either this or the one of VBC to solve. You will still have the same answer. So QAB is equal to 5.0272 multiplies V1 itself is 0.97. Okay. So this implies that this charge in pipe AB is now equal to multiplied by 5.0272 exponential minus 3. Okay, so please take notes. Multiply here by 10 to the power of minus 3 was an oversight. Okay, multiply by 5.0272 by 10 to the power of minus 3 was here. Okay, so we have that answer to be equal to 4.88 by 10 to the power of minus 3 meter cube per second. So this becomes the discharge through the pipe. So if you calculate using discharge of QBC, you find out that the two results will be the same because continuity equation was obeyed. So that's the first part of the question. Second part, we should draw the hydraulic gradient line and the energy gradient line. To do this, the first thing we need to do is to find the values of all the head losses. So let's compute them individually. Head loss due to entrance, we obtain its value to be, let's get it out. So once again, we obtain head loss due to entrance to be 0.0176 V2 squared. So we fall back there, 0.017 V2 squared, 0.0176 V2 squared. Alright, so now we know the value of V2. We had V2 to be 1.17, okay? We had V2 to be equal to 1.17 meters per second. So in place of V2 here, this becomes 0.0176. In place of V2, we had V2 to be 1.17 meters per second. As can be seen here, we had V2 to be 1.17 meters per second. So in place of V2, this becomes 1.17. Remember V2 squared all squared. Alright, so that means by value, head loss due to entrance is equal to, let's punch everything together just to save time, or 1.17 squared multiplied by 0.0176. So we have that to be 0.02. in meters. So head loss due to entrance is 0.02. Mind you, the units are always in meters. Next is head loss due to friction in pipe 1, HF1, and we obtain HF1 to be equal to, okay, over here 1.05 V2 squared. So we also find its value 1.05 V2 squared, and that's equal to 1.05. V2 remains 1.17 all squared. So let's get out the value. So 1.17 squared times 1.05. So that gives us 1.43. We have 1.43 for head loss due to friction in meters. Next is head loss due to contraction. Head loss due to sudden contraction, and we had that to give us 0.05 V2 squared. So this is equal to 0.05. V2 is 1.17 all squared. So let's compute everything together. 1.17 squared times 0.05. So we'll have it to be 0.07. So head loss due to sudden contraction is 0.07 in meters. Finally, we have, okay, next we have head loss due to friction in pipe 2, and we obtain that value to be 1.05 V2 squared, and that's 1.05. V2 is 1.17 all squared, which is equal to 1.17 all squared times 1.01. We have that to be 1.38 in meters. 1.38 in meters. Finally, head loss due to exits or outlets. Okay, exits, and that's simply equal to, we had head loss due to exits. Let's get to it. We had head loss due to exit to be 0.05 V2 squared. Okay, we had it to be 0.05 V2 squared. So head loss due to exit, we had 0.05 V2 squared, and that's 0.05. V2 is 1.17 all squared, which also remains 0.07 in meters. So that's all the head losses. We can now draw the hydraulic gradient line and the energy gradient line. Now, to draw these lines, let's start with the energy gradient line. You start with your reservoir. So you plot out your reservoir. Okay, you plot out your reservoir. Okay, so this is our reservoir. This is the pipeline itself. We want to draw the energy gradient line first. First thing to do, from the pipe surface or from the liquid level, you measure out the entrance energy due to entrance or head loss due to entrance, and the head loss due to entrance HA will obtain it to be 0.02, and every other head losses we have here 1.43 friction at pipe 1. We have here 0.07, then 1.38. So the friction values are the highest. 0.02 seems to be the lowest of all the head losses, okay, which is head loss due to entrance. Remember, HE gave us 0.02 meters. So we measure out 0.02 from the entrance, from the surface of the pipe. Measure out, let's say, from here to this point. Of course, you can do this with a graph or you can do that with a freehand sketch. So this is 0.02. This level from here to this point gives us 0.02. So that's our head loss due to entrance. Okay. So you trace out the head loss due to entrance. You can use broken lines to trace out this point. So just a rough sketch all through. So this height, remember, is 0.02 meters, which is head loss due to entrance. Now the next head loss is head loss due to friction in pipe 2, and we obtain the value over here. Head loss due to friction in pipe 1, head loss due to friction in pipe 1, and we obtain the value to be 1.43. This seems to be the largest value here, 1.43. So what you do is this: you measure out, if it is 1.43, means it's going to be the largest value. Measure out 1.43 from just directly from this side. 1.43. Okay, let's say 1.43 is somewhere around here, let's say 1.43 somewhere around there. So you can also trace this line out. So this height is given as 1.43, which is head logic towards friction in pipe 1. Now join these 2 points, 1.43 and the head logic to entrance, join them together. You have something like this. Join them together. You have this. Okay. Now from this point, next thing to consider is head logic to sudden contraction. And we obtained the value earlier here. Head logic to sudden contraction, the value was given as 0.07 in meters. So you also measure from the contraction 0.07, measure it very just down to this word contracted region, down to the contracted region. So you measure 0.07 down, which is somewhere around here. Okay, so you also trace this. So this height is 0.07 in meters. Alright, so you have this will be the head loss to sudden contraction, 0.07 in meters. Finally, or second to last, you have head loss to friction in pipe 2, which is 1.38. So from here now, from this line, you measure as 1.38. 1.38 should be somewhere down, okay, be somewhere around there. So you join these 2 points, head loss to friction in pipe 2 to this other point, okay, to the contraction, join these 2 points together. I think I should have used a red pen for this. Okay, so you have this line. So these points, you can label this point A, label this point B, label this point C, label this point D. Line A, B, C, D is called the energy gradient line. Line A, B, C, D is the energy gradient. EGL stands for energy gradient line. So this line you've drawn so far is the energy gradient line. Now to draw the hydraulic gradient line is just to follow the energy gradient line. Just take a simple scale, then follow what you have in the energy gradient line and reproduce it. So you can take a simple scale from here. You can simply start from here, just somewhere around here. Reproduce what you have parallel to each of the energy gradient lines. So from this point, I have to reproduce what I have here down to this point. So we draw a parallel line to each of the energy gradient line. That gives you the hydraulic gradient line. So from this point to here, where you have the contraction, then instead of going up now, you have to come down opposite. So directly opposite of what you have in the energy gradient line, you pull this line back, then you trace it down towards the pipe because it's started from the pipe from the reservoir. Trace it from here down to the reservoir. So this line, okay, A, B, C, D, line E, F, G, H is called the hydraulic gradient line. So line E, F, G, H is the hydraulic gradient line, HGL. Alright guys, so that's how you draw the energy gradient line and the hydraulic gradient line for that given question. Okay, so I will see you in the next video with another question. Okay, alright, so that's the diagram. I'll see you in the next video with another question. Thanks.